Hello, everyone. My name is TJ Willits, the moderator for today's webinar. I just wanted to give a few more moments. I could see that there's still several people signing on, so I'm just going to give it another minute or two before we start the presentation. Thank you for your patience. Okay, we're going to begin our presentation. Again, my name is TJ Willits, the moderator for today's event, which is called Nutrient Removal Using Advanced Wastewater Treatment Technologies, focusing on phosphorus and nitrogen removal. Some housekeeping items. Obviously, if you're hearing me, that's great. It seems like your audio is working. And you could also choose to dial in on your phone if you're having issues using your computers, speakers, or your headphones through your computer. There should be a phone number listed on the right-hand side of the GoToWebinar panel where you could log in and hear the webinar audio via your phone. Also, there is a live question panel that you will send. You could send questions to myself and also the panelists for today. So just feel free to enter those throughout today's webinar broadcast, and we'll have some time at the end to try to get through as many questions as possible. One other item to remind you is that at the end of the webinar, when you log out, you'll be given a chance to take a survey. I'd like to encourage you to go ahead and take the 1-minute survey just to provide some information to us on what you thought of the webinar, and then what you could do to maybe recommend some topics for us going forward that you might want to hear. So take the survey at the end. That'll be great. It'll help us and potentially provide you with some valued content going forward in the future. Just one slide about Veolia. Veolia is focused on 3 key main environmental pillars: water, waste, and energy. Today, we're going to mainly be talking about water, of course, with the nutrient removal topic. But Veolia is one of the leading water and wastewater treatment companies and operators in the world. And talking about the industries that we work in, these are the main applications that we provide our customers on a daily basis, everything from water recycling and reuse to ingredient water or raw water treatment, even wastewater treatment, which is pretty much the topic that we're going to talk about, along with bioenergy creation and utility water treatment, as well as the nutrient recovery and also removal. We do that using a variety of tools in our toolbox. We call them our technologies. We have several hundred technologies that we could apply in different customer sites based on the needs that they have or the particular water or wastewater characteristics that they have. So it's that time of the presentation where I get to hand it over to our technologist. I'd like to introduce you to Timur Denive. Timur is the technology manager at Veolia Water Technologies. He obtained a Bachelor's of Science and a Master's of Science in Environmental Engineering, and he's currently working on his PhD also in that same field. Timur brings over 10 years of continued experience working on industrial and municipal wastewater treatment, specializing mainly in biological processes. So at this time, I'd like to welcome Timur to the presentation.
Thank you, TJ. I appreciate it. Hello, everyone. Thank you for being here today with us. This is a very exciting topic. I really like talking about it. It's especially exciting because it involves good technological knowledge and good technologies, and we in Veolia have a few technologies that fit really well in this profile. On the other hand, it could be a little bit tedious and a little bit problematic for people on the other end, because with recent years we see tighter permits, which I'll be talking about a little bit moving forward. But basically, so when we talk about nutrient removal, we will be talking about biological and physical processes to remove nitrogen and phosphorus. We'll be showing case studies for every single technology we will be mentioning. And then we will be discussing about the basics of starting with your nutrient removal projects. And we will wrap up with Q&A afterwards. So why is nutrient removal important? Nutrients, in the definition that we use here, nitrogen and phosphorus, are the main reason for eutrophication of the streams. And eutrophication is the green bloom when you have so many nutrients in the water that plant life takes over, and then we consume all the dissolved oxygen for fish. So it's essential for the health of the surface water bodies. In recent years, we've always also shifted our concentration from just keeping healthy surface water bodies to also making sure to also addressing our health issues. For example, nitrate is famous for causing not only blue baby syndrome, but some cancers, and increased cancer risk has been associated with that. And the main sources for the pollution is the runoff from the surface water and the point source pollutants like industrial sector or municipal sector. And the nutrients from the surface runoff are obviously nutrients that we apply on the surface. Most often it's associated with agriculture. But for the point sources, we talk about residual nutrients from production facilities. So for example, if you have a production facility, you use chemicals, detergents. Detergents are usually high in phosphorus. You might be using some other cleaning products high in nitrogen, or the byproducts of your main processes could also include nitrogen and phosphorus, especially if they're organic in form. So the history of the nutrients removal follows the history of the organic pollution removal in the surface water bodies in the United States, starting with the Clean Water Act. And in the first decade of the 2000s, EPA published federal nutrients criteria. And since then, the NIPTs for direct discharges have been getting tighter and tighter as we go. And as of 2016, there was a renewed call to action to reduce nutrient pollution, because as time progressed, EPA realized that we're addressing the carbon pollution relatively well, but nitrogen and phosphorus, defined as nutrients, the permits have been a little bit more lax, and now they're getting tighter and tighter. And especially in northeastern part of the United States and in some northern states, we're seeing very, very strict nitrogen and phosphorus discharge limits. So if before we used to see 10 to 15 to 25, right now we started seeing municipal discharges with total phosphorus, with ortho-P requirements of less than 0.05 or even lower, and that's very, very tight. And if you don't have direct discharge permit, it doesn't mean that this permit is not going to affect you, because if you're discharging with municipality and you have a pretreatment facility, municipalities are going to be passing the bill. So as you can see, EPA stated that nutrient pollution remains one of the greatest challenges for the nation. And we're seeing the permits for 2020 and 2023 getting very, very tight. I've already said it multiple times, but for the sake of this webinar, we will be mainly concentrating on nitrogen and phosphorus. There are some other pollutants that could be defined as nutrients, and we will also in the future be putting together some seminars on micropollutants and enhanced BOD and COD removal. But specifically for this webinar, we're concentrating on nitrogen and phosphorus in their aqueous form. There are multiple ways we will be removing. We can address nitrogen and phosphorus in water. But today, to keep it short, we will talk about the most commonly used methods. So you can address it biologically, physically, chemically, through ion exchange or degasification. But today we'll concentrate on biology and physical chemistry. And under the umbrella of biology and physical chemistry, we'll be talking about specifically MBBR, ballasted high-rate clarifiers, dissolved air flotation, and disk filters, and how those technologies fit in the overall picture of the nutrients removal. So let's start with the nutrient removal for biological technologies. If you're familiar with Veolia lineup or if you've participated in previous webinars, you're probably very familiar with our MBBR technology. We really like the MBBR technology for its diverse set of applications, but the basic idea with MBBR is that we have fixed film suspended carriers that we put into aerated system, not dissimilar to activated sludge, but instead of keeping all of the solids in suspension, we're providing specific surface area for biofilm to grow on the fixed film media, and that provides a lot of advantages. So today's webinar is not about MBBR, but the advantages are flexible configuration, smaller footprints, high retention of biomass, and also very, very high resistance to load variability. But let's examine how it's going to work for our applications for nitrogen and phosphorus removal. And in this slide, you see the biofilm formation and understanding that all of the biodegradation is going to be happening within this biofilm is something I would like for you to keep in mind as we're moving forward in this webinar. So let's talk about the very basic. When we talk about nitrogen removal biologically, we're basically talking about two subsets of biological processes. So most often, with some rare exceptions, which are important, we see nitrogen in the wastewater in its most reduced form, and that's ammonia. Ammonia, prior to removal, ammonia needs to be converted to nitrate nitrite. And that process is called nitrification. So basically we're taking ammonia and we're providing enough oxygen for ammonia to be converted to nitrate nitrite. And then we put it into less oxygenated environment where through the process of denitrification, we're removing nitrate nitrite into elemental nitrogen. So this picture is the basic for all of the nitrogen removal we will be talking about. And depending on your permit, it would be important to understand where you are in that picture. So for example, here is an example of the flavors company in Michigan, where we had to only remove ammonia. So in this case, we're talking about removing only the first stage of nitrogen removal. Because obviously, as if we need to remove all of the nitrogen and go through nitrification, denitrification, you would need more tankage and more power. So it's important to also know where you need to, what components you need to remove and what your permit is. So on the next slide, we will see that in this application, we've designed the system to only perform the first stage of nitrogen removal, meaning nitrification. So you can see a very variable ammonia load into the system and reliably no ammonia on the effluent. Now, does this mean that we removed all of the nitrogen? It does not. it means that we've taken nitrogen from ammonia form and converted it to nitrate nitrite. But in this case, the permit was for nitrate nitrite, so we performed it in a single stage after carbon removal. Here is another example where we had to accomplish a similar goal. I like this overall outline because a lot of technologies were presented in this application. This is a direct discharge permit wastewater treatment plant facility for a confectionery and chocolate producer in the United States. And I'll be talking specifically about the two-stage MBBR, hydrofloat, and disc filter as we move forward. And for this part of the presentation, only about the two-stage MBBR. Similarly to the Michigan case, we only had to provide nitrification for this particular client. And similarly to the confectionate, to the Michigan case study, we have a high variability of ammonia load coming in and reliably no ammonia on the effluent. When I was talking about nitrification, I talked about a full oxygenation step where we take all of the ammonia and we convert it fully to nitrate nitrite. And that process is very well studied and we've known about for a very long time. However, in the past 25 years, scientists in Delft in the Netherlands discovered the naturally occurring phenomena of a specific type of microorganisms that is called anaerobic ammonia oxidation. It's similar in concept to nitrification step, except it's very different in its metabolic pathway. So how do we use Anamox in our patented Anitamox MBBR system? Instead of converting all of the ammonia to nitrate nitrite, we provide only enough oxygen to convert some of the ammonia to nitrate nitrite, and then we rely on the specific Anamox microorganisms that are secured in our K5 carriers here to convert ammonia and nitrate into elemental nitrogen and a little bit of nitrate on the effluent. It's a very elegant process and it has a few niche applications where it's really nicely applicable because it consumes approximately 60% oxygen. It means that you can accomplish similar nitrification efficiency for your wastewater in similar tankage but using less oxygen. And the advantage that we have with our carriers is that we don't need to provide several steps in tankage to provide proper metabolic pathways. Everything that we want to accomplish, whether it's nitrification or Anamox or floccular system, could be accomplished all within the biofilm on the chip itself. So what you see on the left, you see a full biofilm where we have NO2 limitation with our with the penetration of oxygen through the biofilm, and through additional configuration on the right, we remove that limitation step into the suspended stage from the fixed stage and provide the entirety of the biofilm for the Anamox microorganisms to accomplish the ammonium oxidation. Here is a very nice case study where we used our Anitamox on the outlet from our anaerobic membrane bioreactor to remove ammonia. With the influent concentration of nitrogen up to 350 milligrams per liter, we were able to accomplish less than 30 milligrams per liter in total nitrogen by relying on Anamox only, and less than 10 milligrams per liter of ammonia. And here are the results. The black line on the graph is prior to introducing the Anamox. process into the system, the Anitamux system, prior to starting it up. And after it was started up, as you can see, influent ammonia didn't change throughout. We were seeing approximately 165 to 210 milligrams per liter of ammonia coming in. And as soon as the system was turned on, the effluent ammonia was in the range of below 30 milligrams per liter. So now let's switch gears a little bit and concentrate on phosphorus. So when we're talking about phosphorus removal, most often we're talking about removing phosphorus in its reactable form, so in ortho-P form. Here we're talking about applications where we have a lot of phosphorus, and as we move forward, we'll be talking about smaller and smaller concentration of phosphorus. So when we're talking about biological phosphorus removal, we're talking about a specific set of anaerobic and aerobic system where we, through providing high acidification step, selectively grow a biomass that instead of holding approximately 1 gram per 100 grams of biomass of phosphorus, can accumulate up to 30 to 40% of its mass in phosphorus. So all we're trying to do in the biological phosphorus removal step is to selectively grow a biomass that is able to hold more phosphorus in it. And then by removing the biomass, we're selectively removing the phosphorus. And this is very interesting in high phosphorus concentrations like dairy, ethanol stillage, and where you have very high influent phosphorus concentration, very low permit, and you want to cut out the chemical phosphorus precipitation costs, which we will be talking about later on in the presentation. So here's a nice example. We're not able to hit very, very low concentration of phosphorus that we can hit with the physical chemical precipitation. But what we can reliably accomplish 30 to 40% removal of ortho-P through the biological phosphorus process. And that will obviously be directly transferred into your operational expenses by reducing them by the same amount you would be removing using the bio-P. So here's a nice example. As you can see, effluent nicely trails the influent concentration, but you constantly nicely removing approximately 30 to 40% phosphorus here. But most often, if we do not require the roughing stage with the bio-P where we can save on our capital, when we talk about phosphorus removal, we talk about chemical precipitation. And here I introduce you what we call phosphorus removal dilemma. What you're seeing here on the graph is the log concentration of coagulant. In this case, it's iron-based coagulant. It could be aluminum as well, but usually in order to normalize the data, we will be talking about iron coagulant. And on the log scale, what you see is the consumption on mole per mole basis of iron per the amount of phosphorus removed. And your x-axis is the concentration that you're trying to accomplish. So if you examine the stretch from 1 milligram per liter of ortho-P to 10 milligrams per liter of ortho-P, you will see that mole-to-mole ratio is almost linear. So you will need approximately stoichiometrically 1 mole of iron per mole of ortho-P. Obviously, in engineered applications, we like to overdose a little bit, but the relationship is fairly linear. So let's say you have 30 milligrams per liter of phosphorus in your influent, and your discharge in 2023, your permit is going to be 0.05. If you try to remove it all chemically, you will be hit with a dilemma with the fact that if you need to go to less than 1 milligram per liter, your consumption rate, the closer you get to 0.1, increases on a logarithmic scale. So by the time you need to get down to 0.1, your molar ratios now could easily hit 100 moles of iron per mole of phosphorus. So this is an excellent thing to ponder about when you think about phosphorus removal. So in case of 30 milligrams per liter, we would always recommend roughing out approximately 10 to 15 to 20 milligrams per liter using BioP, and then staging your phosphorus removal, which is what I'll be talking about next. So here is an example of ActiveFlow. ActiveFlow is a very well-known Veolia system for ballasted flocculation. It has very high contact rate between the chemistry and the wastewater, which substantially improves your coagulation efficiency. And it's very important in case of phosphorus, especially knowing that first graph that I was talking about. So here you will see we introduced the polymer that goes through a very high mixing zone coagulation and flocculation, and then the ballasted flocculation using sand rapidly precipitates all the flocks that are formed, and then sand is separated through hydrocyclone, which introduces even more mixing into the system. So let's examine here a very interesting case study for a dairy wastewater, where we were working to achieve less than 1 milligram per liter of phosphorus on the effluent from our aerobic system. So look at the TSS concentrations we're talking about here. Since it's an activated sludge system that was ran at a very high concentration of TSS, the TSS on the left is in a range of 5 to 6,000 milligrams per liter with a total phosphorus of close to 200 milligrams per liter. And in a single stage of active flow for this dairy, we accomplished two things. We accomplished both phosphorus removal and suspended solids clarification for this activated sludge process. And in a single stage, we were able to achieve less than 50 milligrams per liter of TSS and reliably less than 20, actually, as you can see. And total phosphorus was removed to under 1 milligram per liter, which I think is a very interesting result, and it has very nice application throughout the industry. In some cases where active flow is not what we would need, we will be talking about dissolved air flotation. Now, dissolved air flotation is a very common technology to remove suspended solids and BOD. However, we do know that we use coagulants and flocculants here. So we introduce coagulant and flocculant, and then we relies on the rise rate of saturated of oxygen or air saturated water to float all the flocks on the top where we remove them. And with the proper selection of coagulants, we're playing a very interesting game here. So this is still same that candy manufacturer that I was talking about in nitrification case. But if we choose the proper coagulants, a metal-based coagulant, while removing suspended solids, DAF will also obviously achieve removal of phosphorus. Here is total phosphorus on the effluent to DAF from the candy manufacturer, around 10 milligrams per liter, and we can reliably hit that less than 1 milligram per liter of phosphorus on the effluent most of the time. But let's say that's not enough for us. So we polished it out to less than 20 milligram per liter, where around 1 milligram per liter of phosphorus, and we still need to remove it down. Well, disc filters come into play. So disc filters are smaller, more compact, more mechanized technology, where you're relying on a physical barrier to separate solids. And if you introduce more coagulants prior to disc filter, you will be forming tighter flocks, and then you're removing them through the barrier. And here's the examples of how we can stage the disc filters, but the next slide is where we're going to be concentrating on with the dosing. So here I'd like to spend a little bit more time just discussing how great the numbers are, and also wrapping up everything that we talked about with the phosphorus. So as you saw with the DAF effluent, we got close to 1 milligram per liter, but let's say your permit requires less than 0.5. which is not uncommon with the upcoming permits. And we also remember that once you go to less than 1 milligram per liter of phosphorus, your molar ratios jump substantially up. So here's an excellent example. You see so on the right side with the total phosphorus, you see 3 columns for the influent phosphorus. Those are 3 different labs, so don't get confused with K, SP, and NL. They're just different laboratories trying to measure the same thing, which is basically influent phosphorus into the disk filter. And then effluent is also 3 lab effluent for the disk filter, where we were able to get close to 0.05, which I think was the permit here. So we accomplished it, but also look on the left into the molar ratio, and you will see where we had to spend 20 to 40 moles of metal-based coagulant per mole of phosphorus to remove it to such low concentrations. So in this approach, as I said, we staged the phosphorus removal. First it was DAF, and then we applied the disk filter to get into this very, very low concentrations and not to overdose the coagulant in a single stage to achieve the same results. So what would get you started with a nutrient removal project? Let's go through our checklist. As I presented in the beginning, if you operate wastewater treatment plants in industrial facilities, you're probably facing renewed permits right now. A lot of facilities are looking at renewal of the permits, and the new permits that are coming starting this year and into 2023 will have much higher nitrogen and phosphorus limits. So while before you probably didn't have to think about, for a lot of our clients, they now have to consider nitrogen and phosphorus even without changing anything in their system. Alternatively, your current system is not performing well and you would like to optimize it, or you know that in the future you will be producing a new line of product, or you will be expanding your production and introducing new permits. For the expanded production, we're introducing new loads into your wastewater treatment plant. So right now would be a very good time to start planning not only for your conventional BOD and TSSs, but also starts planning and talking to your permit issuing agency about nitrogens and phosphorus. And if there's going to be challenges, obviously we're here to help you out with that. So TJ, I think this is it. We can wrap up and see the Q&A section, right?
Thank you, Timur, for that presentation. Yes, it is time to transition from the main portion of our presentation to our more interactive section of the presentation. As I mentioned earlier, there's a Q&A question panel on the right hand of your screen likely. And if you have any questions for Timur about today's presentation or related to water or wastewater treatment, I'd encourage you to go ahead and type that in there, and we're going to try to get to as many as possible. And while you may be doing that, I just wanted to remind everyone that we are going to also have a survey, and the survey will pop up at the when you leave the webinar. And if you could just take a few moments to go ahead and fill that out. Like I said, it'll help us plan for future content from our technologists that we have here at Veolia Water Technologies. Okay, I got a question here, and the question is can you walk through where you would identify the best place in choosing nitrification, denitrification as a method for nutrient removal?
Absolutely. So I will start talking about nitrification, denitrification if I see either one of the two things on the permit. You're either permitted on the total nitrogen and you have nitrogen on the influent, or your permit talks about both ammonia and nitrate nitrite. So I've seen both. When you're talking about total nitrogen, I immediately know we cannot just nitrify, because if they measure total nitrogen, they will measure nitrate nitrite, and your total nitrogen is basically not going to change. So we will need to go to nitrification, denitrification in that case. Or if your permit states that TKN or ammonia and nitrate nitrite at the same time, which effectively is the same thing. Basically, where they're telling you, we cannot receive this amount of ammonia, neither can we receive this nitrate nitride. So all that is left for me is to remove the nitrogen fully into its elemental form, which is nitrogen gas, which is going to fly out from your basin and go through the full nitrification, denitrification step, which needs to be very carefully designed. I see all too many cases where nitrification, denitrification is under design, and people are battling the losing battle of either nitrifying or trying to optimize their denitrification and not meeting their total nitrogen permits.
Okay, thank you for answering that. We have some additional questions coming in related to biological treatment primarily here, but we have someone wanting to know about this kind of treatment in relationship to wastewater that might be high in salinity.
So salinity is always something that we need to take into consideration. So total dissolved solids, depending on the type of solids that they are, could interfere with the biological process. So we need to know approximate ranges that we talk about. We have some applications. We have pickle juice applications for the dill pickles with very high concentration of TDS. In those cases, we also look at the full chemistry and trying to figure out to what degree TDS is going to interfere with our biology. And it could, at very high concentration, TDS, like with any salt, at first would start retardation of biological processes, and then so they become the processes become slower, and then at some point high salt concentrations would fully stop the biological processes. So it's highly dependent on your concentration. If it's just the concentration that would slow down our process, we will just have to upsize the overall system size to meet the slower metabolic rates. If the concentration of salts are so high that we cannot address them, we will have to look into alternative treatments such as crystallization, evaporation, or reverse osmosis, depending on the application.
Okay, another question here. It looks like more of a retrofit kind of question, but it says, would any of these technologies for total phosphorus removal work with an ASB instead of activated sludge?
Absolutely. The answer is most definitely. And we have applications with ASBs where we bring over, I mean, as long as we can ensure continuous flow into DAF would work, similar with active flow. So we might need to put an intermittent vessel or something, but we sell the systems on the effluent from a vast variety of upstream systems, including ASB.
Okay. This question we have from one of the attendees is that we have incoming water used for non-contact cooling water that comes into the facility with chlorine and phosphorus levels higher than the new permit discharge allows.
Yeah.
Where and what would you use to remove the phosphorus from this non-contact cooling water?
I've seen these cases. I've seen a couple of cases in Wisconsin where there's the case that their influent water from their well does not meet their direct discharge. Disc filter in this case is an excellent technology. It can take very high flows at low solids and variety of temperatures. So all we need to do, we provide a disc filter with well-adjusted coagulation, and we monitor our chemistry well, so we don't have a lot of carryover, and we meet our discharge permits. We have, I think we have a lot of application for disc filters on cooling tower loops. There's, I think, in hundreds.
Okay. Another question here. I'm just going to try to get through as many as possible. It's an application question. Do we have any examples or references or case studies related to corn wet milling facilities?
Corn wet milling facilities for nitrogen. Oh, I assume this is about nitrogen and phosphorus removal. We have a lot of examples where we applied nitrogen and phosphorus removal through various technologies at dry mill facilities and I think wet mill facilities as well. Yes, most definitely. the spread on the dry and wet mill facilities is, the past 25 years or something, because some of them are a little bit older, but we definitely have worked with them.
Okay, another question, and it says that if we use seawater for flushing, is it easy to use biological treatment for phosphorus removal?
As I mentioned in the TDS conversation, we just need to look at the concentration of salts. If it's just the seawater, it will be strongly bacteriostatic. So using biology is going to be a little bit more difficult. If there's other streams that dilute the salt concentration, so it's not as bacteriostatic, we can go biological. Otherwise, I would recommend going physical chemical, and high saline wastewater for active flow and disc filter are very well studied. A lot of our aquaculture applications use active flow and disc filters for nutrients removal from saline wastewater.
Now, switching over to the other portion, the physical chemical portion of our presentation, the question that we have in front of us here is that, are any of the flocculants available for nutrient removal biodegradable?
I think the answer is yes. We have a lot of recently developed green Hydrex lines. I don't know all the numbers, but I know that in the past 10, 15 years, there was a big push for it, and some of them are biodegradable. They might not be as effective, but I know that we've developed a lot of them that are biodegradable.
And just something to add too is I know that we have some applications as well as that they're using it for byproduct for animal feed as a part of the removal as well.
Yes, correct. Yes.
So another question for physical chemical, is active flow practical flows up to 7,000 GPM?
Active flow is best fitted actually for higher flows. Absolutely. So our active flow is installed at largest municipal wastewater treatment plant facilities with massive flows. I would actually not consider active flow I would carefully consider active flow for flows under 250,000 gallons per day. Actually, that's where the smallest systems start unless there is very high solids. So active flow has been historically designed for huge municipal facilities with very large flows.
Okay, it looks like we're got through all of our questions that we had asked there. Oh, just one more came in. How do you identify when using BioP over some of the other biological technologies?
So BioP, once again, so all I'm trying to do with BioP majority of the time is to shave off the high phosphorus. For example, if you have 5 milligrams per liter and you need to meet the discharge of 1, I probably wouldn't even consider it. I consider a sweet spot for BioP when I have high CODs, let's say it's over 2,000 milligrams per liter, and also high phosphoruses. So I'm coming in at phosphorus about 50, about 100 milligrams per liter, and I know I need to meet the discharge of 1 milligram per liter, 1 to 2 milligrams per liter, and maybe even lower than that. So I know everything that I can remove biologically, I will not be paying in cost of chemicals. So I come in at 150, I know I can remove 30-40% biologically, and the rest will still need to be removed using chemistry. I will most probably fit economically with a return cost of less than year and a half on operational expenses. I would fit in biological phosphorus removal pretty nicely.
All right, thanks for walking us through that analysis of feasibility for BioP. Looks like that we're just at the planned end time for our presentation. I want to thank everyone for joining us here to learn a little bit more about these exciting technologies for nutrient removal. They're going to be more and more important and critical to the environment and your industries as we go forward, and we see those tighter NIPD's discharge permits looking for lower levels of nutrients. And I would also like to thank our presenter, Timur Denive, for spending time with us and preparing this technical presentation. We really appreciate you as well. If you have any questions, and if you have any additional questions, my contact is up on the screen, and I could connect you with one of our experts if you have any issues. And again, thank you for being here. Be on the lookout for additional invites going forward for some of our upcoming seminars and webinars as well. Have a great week, everyone. Take care.
Bye.